All right, today we are going ghost hunting, but in the world of AI. We're on the trail of a concept from way back in the 1970s that, believe it or not, is secretly running the show in the tech you and I use every single day. So let me ask you something. What in the world connects the way Google gives you those slick, organized search results, the way ChatGPT seems to just get the context of what you're asking, and even how your doctor's office keeps all your medical records straight? The answer is, well, it's definitely not what you think. Nope, it's not some brand new cutting-edge algorithm. It's actually a foundational idea from 1974, a concept that a lot of people in AI wrote off as obsolete years ago, but it turns out it's been hiding all around us this whole time. This old ghost in the machine is a system for representing knowledge called frames. And honestly, if you really want to understand how AI organizes and reasons about the world, you've got to understand this. Okay, so what exactly is a frame? The easiest way to think about it is like a reusable template, or maybe a blueprint. It's just a structure with slots for information. Think of these as categories like name or color, and fillers, which are the actual values, like sparrow or brown. But here's the real magic. Frames can inherit properties. So you can define a bird frame just once, and from then on, every new bird you create automatically knows it's supposed to have feathers. It's built in. Now, I know what you're probably thinking. Okay, that sounds kind of old-fashioned. Surely we've moved on to better things. But that's what's so fascinating. Frames never actually went away. They just got incredibly good at hiding in plain sight. In fact, frames are the literal backbone of systems where knowledge is stable and has a clear hierarchy. Schema.org, the thing that gives Google all those rich, structured results, that's a massive frame system. The same goes for the electronic health records that organize patient data, the huge ontologies that classify every known gene function, and even the software that configures complex industrial machinery. They all depend on this kind of predictable, structured knowledge.
But here is the biggest surprise of all. The core ideas behind frames are even at work inside the most advanced AI we use today. Yep, I'm talking about large language models.
Check out how this works. When you ask something like GPT-4 to describe a Tesla Model 3, it kind of dynamically activates a vehicle frame in its mind. It starts looking for information to fill in slots like price and features. But if you then ask it to describe Tesla the corporation, it instantly switches gears, activating a company frame and starts looking for a CEO and market cap. It's using these invisible templates based entirely on the context you give it. Now here's the crucial difference. Classic frames were built by hand. Human experts painstakingly coded every single rule. LLMs, on the other hand, learn their frame-like structures from the patterns in trillions of words of text. And this leads to a really critical distinction. When a classic frame doesn't know something, it just tells you the slot is empty. But when an LLM is uncertain, it hallucinates. It just makes up a plausible-sounding filler to put in the slot. And that right there brings us to the core trade-off of these systems. They are absolutely brilliant at what they do. But at the same time, they can be incredibly fragile.
Their biggest strength, their superpower, is that automatic inheritance. Say you're building a medical diagnosis system with frames. You define a frame for viral infection. Now, any new disease you add under it, like COVID-19, automatically inherits all the properties of a viral infection. In a normal database, you'd have to write all these manual queries to link everything together. Frames they just know.
But, and you knew there was a but coming, that same rigidity that makes them so powerful is also their greatest weakness. The real world is messy, it's complicated. And when a situation doesn't fit perfectly into one of those predefined boxes, frame systems don't just bend, they break. Here's the perfect example. A self-driving car. What is it? Is it a vehicle? Is it a robot? Is it a piece of software? Well, the answer is yes, it's all of the above. And for a rigid frame system, that kind of ambiguity can cause total paralysis. This creates a classic issue in computer science called the diamond problem. Imagine your self-driving car system inherits rules from a vehicle frame, which says a driver is required. At the same time, it inherits from a robot frame, which says a driver is not required. What does the system do? It has a direct contradiction in its core logic. The whole thing just grinds to a halt until a human engineer steps in to write a special exception. And that need for a human to step in and fix things, that points to the number one reason frames didn't just take over the world. They can't learn. Every single rule, every connection has to be painstakingly coded by an expert.
This was the heart of the great debate in early AI: symbolic, hand-coded systems versus systems that learn from data. That massive effort is why machine learning eventually won out.
But the story doesn't stop there, because today we're seeing the rise of a really cool new solution, a kind of hybrid brain that combines the best of both worlds. So here's how it works. A hybrid system uses a frame for what it's great at, defining strict rules. For example, a laptop frame must have a CPU, RAM, and a display. But, and here's the genius part, instead of storing the CPU name as just plain text, it stores it as a vector embedding, which is a rich mathematical representation of its meaning. This lets the computer understand that Intel i7 and AMD Ryzen 7 are conceptually similar, even if the words are totally different. What you get is structure plus flexibility.
And hey, this isn't just some academic theory. In real-world A/B tests, these hybrid systems boosted the relevance of product recommendations by a massive 43%. You get the logical rules you need and intelligent, fuzzy search capabilities. It's a game changer.
So it's pretty clear that frames aren't some obsolete idea we left in the past. They're a foundational concept that has just continued to evolve in fascinating ways.
Let's just break down the whole landscape. You've got pure frames, which are great for stable, predictable things, but they're slow and rigid. Then you have graph databases, which are fast and flexible, but need more manual setup. Then there's pure vector embeddings, which are insanely fast for finding similar stuff, but have zero logical structure. The hybrid system really does find that powerful sweet spot in the middle.
And this chart just drives that point home. I mean, look at this. You can see the dramatic trade-off. On one end, you have the logical completeness of frames, but they're taking over 2 seconds for a query. On the other end, you've got the mind-boggling speed of a pure vector search, happening in just a few milliseconds, but with no real structure. The future is all about intelligently combining these approaches.
So I think this is the ultimate takeaway. That 1974 innovation, it didn't die. It just dissolved and spread into the very foundations of how we make computers understand information. Think about it. The core concepts, inheritance, default values, attaching little bits of logic to data, these ideas are now just fundamental parts of the semantic web, modern software design, and yes, even the way large language models process information. The ghost is, without a doubt, part of the machine.
So I'll just leave you with this final thought. If a 50-year-old idea is this critical to our most advanced AI, what other old and maybe forgotten ideas are quietly hiding in the technology you're using right now? Thanks for digging into this with me.